I would like to thank the organizers for letting me present my work here, and it's been a very good workshop. What I will tell you about today is mainly based on these two papers, so this recent one that appeared on the archive last month, and a lot of the groundwork was laid in this paper with Ilias that dates back from last December. Start with some motivations, then we'll explain the philosophy of the classification of these infrared phases. I will very briefly comment on what type of solutions you might get, describe what sort of deformations you have around them, because it's important to make sure that these are actual phases that you can reach in the infrared. Then I will talk a little bit about the optical conductivity and the spectrum of fluctuations, and I'll have some comments about minimal surfaces in those geometries. So the motivation is basically coming from condensed matter systems where you see scaling laws, and those scaling laws are presumably related to the fact that there's a quantum critical point somewhere on the zero temperature axis, and it's supposed to be responsible for all this scaling, these anomalous scaling properties that you see, for instance, in the strange metallic phase of all these high TC superconductors. And I would like to think that if there's a scaling that appears in transport coefficients, for instance, it's probably a good hypothesis, a good working hypothesis to assume that this scaling will also appear in any gravitational dual that might be lying in the same universality class as these systems. So this is my main motivation for looking at geometries which have scaling properties in the infrared. So it's not completely obvious what is supposed to happen in the IR. We know very well what's going on in the UV, because usually we assume that this is ADS4, even though you can do other things like Lifshitz or Schrödinger. But so the UV, we understand how it works. But just specifying data on the UV doesn't really tell you much about the infrared itself. There's many different possibilities that might occur. And so what I want to do is to try to constrain a little bit what might be going on here, and what are the physical consequences of the various infrared geometries that you might have. Another important point is that there might be several such phases that are competing in the infrared. And they might break different symmetries, they might break translation symmetry, but not necessarily. The main issue is that unless you have some idea of which phases are there, then you can't really know for sure that you've actually found the dominant phase in the infrared. So ideally, what you want to have is some sort of classification that would tell you, so this is my theory, this is the symmetries that I'm interested in, and having specified that I know that have, for instance, these three phases, and that those phases might be dominant in different parts of the phase diagram. But holographically speaking, it's very hard to actually, shooting down from the UV, know for sure that you've scanned through the whole array of possibilities in the infrared. So what I want to advocate is a sort of bottom-up approach where you start from the IR and you look at what are the various possibilities, you constrain them such that you can actually reach the UV, and then you determine in which regions of the phase diagram they are the dominant phases. So this is the sort of philosophy that we've been trying to implement in this program that we've been working on with Ilias and several other collaborators for a couple of years now. And so the idea is you introduce a set of operators which are irrelevant in the UV. They don't destroy your ADS4, but then they become relevant towards the infrared, and those will tell you what are the different possibilities for these infrared geometries. Then you will write down an effective action that describes these IR dynamics, because maybe not all pieces in your UV Lagrangian are important there. Maybe you can forget about some of it. Then, like I said, you analyze Einstein's equations, and you look for the different zero temperature phases, and for that you specify what are the symmetries typically. Next, what you do is you deform around these zero temperature solutions, because you want to make sure of two things. The first thing is that since we're doing holography, you want to make sure that you will be able to heat them up. So you want to make sure that you can turn on some small non-zero temperature around them. So that would give you a first condition that you have to satisfy. And then the second condition has to do with basically counting integration constants in the IR, counting integration constants in the UV, make sure that you have the right count on both sides, and that in the infrared, the number of integration constants that you turn on give you the right number of irrelevant mode that will allow you to shoot up. Unless you have that, then probably your fixed point or your infrared geometry will not be a stable endpoint of your RG flow. So you might still be able to reach it if you fine-tune some coupling in the UV, but it might not even be the case. I mean, you might not even see it. So if you're not going to see it, then you can probably forget about it. And then the last step, the next step is to actually construct the flow. So sometimes you can do that analytically. There's a whole machinery of how to find solutions to Einstein's equations, but that's typically hard. So now people resort a lot to numerics. And once you have your solution, you can actually work out what are all the thermodynamic quantities. In order to do that, you need to know the UV to compute the free energy, for instance, and that tells you in which regions of the phase diagram you might have a thermal phase transition or even a quantum phase transition if that phase transition happens by varying not the temperature but some other coupling that you have in the UV. Okay, so I'm going to start describing the first step, which is to talk about the symmetries. And we'll first describe a set of symmetries that parameterize solutions that are called hyperscaling. So in this talk, I am not going to break translation or rotation invariance. Elias has told you a little bit on Wednesday what happens when you start fiddling around with breaking translation invariance. So here I'm going to take a step back from that direction, and I'm going to try to make several other steps in another direction where you keep translation invariance. So what I will do, though, is generically allow for Poincare symmetry to be broken and still require that there's some invariance, so there's some rigid scaling like this, where time and space scale anisotropically, and this anisotropy is parameterized by this exponent z. So z is usually called the dynamical exponent. And then it's not very hard to see that if you insist on symmetry under this transformation, then this specifies this metric ansatz for you. And this is typically what we call Lifshitz in holography that I'm sure you know very well, and that you can embed in a variety of models using a variety of matter contents, whether it's p-forms, massive vector fields, even some runaway scalars. And of course it reduces to very well-known solutions for specific values. So z equal 1, you just restore Poincare symmetry, so this is just ADS4. If you let z go to infinity and you rescale this r coordinate, then basically this factor here collapses and you recover ADS to cross R2 or RD. Here, whenever I'm talking about d in this talk, I mean the number of spatial dimensions in the boundary. And if z is non-zero, different from 1, then that's typically Lifshitz. And those solutions are we call hyperscaling, because if you work out what is the scaling of entropy with temperature in those backgrounds, you will typically find that it scales like t to the d of z, which is exactly the same relation that you might have gotten from dimensional analysis, and this is why they're called hyperscaling. If you want to complicate things a little bit, then we might want to violate this hyperscaling. And basically that means that we break scale invariance in the metric ansatz that I had on the previous slide, just by introducing this conformal factor in front, which is parameterized by this theta exponent, which I will call the hyperscaling violation exponent. Now you see that this metric is only covariant under that scaling, and if you work out what is the scaling of entropy with temperature, then you find that it scales in this effective dimensionality, which is actually d minus theta, so it's the usual dimensionality corrected by this hyperscaling violation exponent, and it's been studied quite a bit now. And what's nice is that this effective dimensionality, you can actually trace it back to some proper dimensionality of spacetime if you use various kk lifts, because then that solution will typically become hyperscaling, but in a spacetime which lives in 2 plus df instead of 2 plus d. Now, I will use this sort of effective holographic action. So I won't show you in this talk any specific solution. If you want to see the solutions, you can talk to me or look in the papers, they're all there. But I will try to model things in such a way that it gives me some sort of common framework and try to extract universal statements. So typically what I want is gravity, of course. I want a gauge field because I want to be at finite density. and I will allow for a scalar in order to reach those hyperscaling evaluating solutions. And I've also introduced, so here I've introduced a source term for the Maxwell field. Sorry, I'm getting a little bit ahead of myself. Let's keep that for the next slide. So allowing for this type of action, you have several competing terms in the effective potential for the scalar. And so now your scalar can do either of two things. Either it goes to a constant that will extremise either the full potential or parts of it. So typically you get ADS4, Lifshitz, ADS2 cross R2, depending on whether you extremise the whole thing or only parts of it. Or it might display logarithmic running. And then I can actually simplify my problem because I will make a choice. I will pick those couplings to reduce then, in those cases where the scalar runs logarithmically, to reduce to exponentials. That's for two reasons. First, because that exponential potential appear quite a lot in top-down models. And the other reason is that they make the resolution of Einstein's equation much simpler. You don't have logs of logs R that are floating around, so that's much nicer. Right, so let's come back to this source. So by this term, I mean anything that will appear on the right-hand side of Gauss's law in the IR, because I want to allow myself for Gauss's law to be broken in the infrared. This does not necessarily break the U1. It depends on the specific model that you're looking at. But what I want to do is to source Maxwell's equation. And so typically what I will say in this talk applies for any of these three kinds of models. So it's quite generic. It could be some massive vector model, which you can consider as describing the infrared asymptotics of holographic superfluids, for instance. It also applies to electron stars. And maybe I should say that electron stars in which the local chemical potential scales with R, scales with the radial coordinate in the infrared, so it typically diverges. And also theories where the source of, on the right-hand side of Maxwell's equation, will come from a magnetic field via some Chern-Simons coupling. So the reason why I want to have a source on the right-hand side of Maxwell's equation is that I want to be able to describe these two different situations where the electric flux either comes from a charge horizon or from some charged matter that is sitting in the bulk, or from some magnetic field. And the motivation for this is that we know that zero density event horizons describe the confined phases. So we'd like to be able to think about charge horizon as describing confined charge carriers, which are called fractionalized phase in condensed matter language, whereas charge fields in the bulk will describe the confined phases. In order to parameterize that, I will introduce this new scaling exponent, which I call the cohesion exponent, simply because it tells me how the electric flux is scaling in the infrared. So if psi equals 0, then I have a fractionalized phase because the flux is constant. If psi is non-zero, then the electric flux will vanish. So now I can play the game of seeing what happens when various operators are being relevant or irrelevant, and what that means in terms of the solutions themselves. So typically, if I have a relevant current, I will break Poincare symmetry, and that will lead to an isotropic exponent, which is different from 1. And that we've seen explicitly already in this paper by Gupson and Neller in 2009, where they were playing around with the dimension of the dual current and seeing that you would interpolate between either ADS4 or Lifshitz asymptotics, depending on that dimension. Now, if you have a relevant scalar, you will break scale invariance, so that will typically give you these hyperscaling evaluating solutions. And if this source becomes relevant, then that means that typically the phase will be cohesive all the way to the IR. There will be no electric flux that emanates from the horizon. So there's one last ingredient that I want to introduce, because I've told you about how the electric flux might scale, how the metric might scale, what the scalar might do, but I haven't talked about what the electric potential might be doing. And it turns out that it's very useful to parameterize how much the electric potential itself deviates from invariance under the Lifshitz scaling that I had. And this deviation, so if you forget about this zeta and this psi, then the electric potential would be invariant under the Lifshitz scaling. That's typically what happens in the massive vector case, without any scalars. But here I'm introducing this zeta minus xi. So xi we've already seen, it's the scaling of the electric flux. And now I'm introducing a new scaling exponent, zeta, that for now I call the conduction exponent. You don't know why, you will see in a few slides. And the point is that, like I said, if xi equals 0, then it parameterizes directly the violation of this scaling. If it's non-zero, then it's the combination of the two which parameterizes the deviation from that scaling. So in a sense, you can think about it a little bit similarly to what theta does for the metric. So this is the slide where I describe the solutions. This is as explicit as I will get about the kind of solutions that I'm describing. So they broadly fall into two classes of two very distinct cases. Either the current is relevant in the infrared, and then you find that the dynamical exponent can be chosen at will, but this conduction exponent is fixed to this particular value, theta minus d. On the other hand, if the current is irrelevant in the IR, then the dynamical exponent is 1, because you don't break Poincare symmetry, everything is relativistic in the infrared. But then this conduction exponent zeta is arbitrary. And all the solutions can be classified in these two cases, and this is completely independent on whether they are fractionalized or cohesive or violating hyperscaling or not. So now I want to ask the following question. Given that the form of the metric can be universally parameterized in terms of this theta and this z, that if I look at how the free energy or the entropy scale in function of the temperature, that's only fully parameterized by theta and z, that if I calculate, for instance, the entanglement entropy using the Ryu-Takayanagi prescription, because everything here is static, then I will find that it only knows about theta. So what can I do in order to see where all these extra exponents that I had actually have any impact? So I will look at different observables that are sensitive to this. The first one is the scaling dimensions of the operators in the IR. So in order to determine that, basically what you do is you take your zero temperature solution, you deform it with purely radial static deformations. And that will tell you first this whole thing about whether you can shoot from the IR to the UV with these solutions. But it also will give you the dimensions of the out of the power of the mode. And typically these modes, they come by pairs, so beta plus minus. And they always sum to this value, d plus z minus theta. And this is exactly what you might expect on dimensional grounds if you think about inserting an operator in the infrared. And so there's a source, this is the operator itself. And you know that because there's some effective dimensionality df, then this z plus df is exactly this d plus z minus theta. Now, another thing that you will find is that there's always a universal pair that you will always get that. There's a marginal mode, which is just rescaling of time. And then there's a universal mode, which is d plus z minus theta, which corresponds to putting the solution at non-zero temperature. Yeah. Really? However, so for the other modes, that are the modes that you have to make sure that they are irrelevant, so typically this nu here will depend on all these parameters. So all these parameters will show up in the dimension of the operators. The next thing you can do is calculate the optical conductivity. You do that using the usual techniques. I won't say much about that because it's been very well explored. There's a delta function at omega equals 0 because, of course, we're not breaking translation invariance. And if you work through the calculation, you will find in those cases that in these two classes, the real part of the conductivity scales like that. So if z is different from 1, then you see that everything is still parameterized by theta and z, whereas if z equal 1, then this zeta starts appearing. So that's why I'm going to call that the conduction exponent. A very nice thing is that you will find that these two powers are always positive if you just require, for instance, the null energy condition, thermodynamic stability, and the fact that you have this non-zero temperature deformation which exists. So that's quite good, because this is what you would expect for linear response theory. It's supposed to vanish at omega equals 0. But given these two expressions, it's very tempting to conjecture that there's some universal way of bringing these two classes together which would read like that, because then it reduces to the correct thing. But it's a conjecture. Now you can also look at the spectrum, because when you calculate these conductivities, you reformulate everything as a one-dimensional Schrödinger problem. So you can look at the Schrödinger potential itself, which is always 1 over rho squared, where rho is this Schrödinger coordinate. And a very nice thing is that you will find that if you impose thermodynamic stability, I should speed up. If you impose thermodynamic stability, then basically the spectrum will always be gapless. So again, this is quite consistent with the fact that these powers here are positive, and this is also sort of what you want. Let me skip that slide and come to the questions about the minimal surfaces. So I was mentioning a few things about entanglement entropy, and if you calculate the entanglement entropy in these hyperscaling violating spacetimes, then it was shown that there's a very specific value of the hyperscaling exponent, hyperscaling violating exponent, which is d minus 1, where the entanglement entropy that you get scales logarithmically with the size of the subsystem. And that was conjectured to be due to some hidden Fermi surface of fractionalized degrees of freedom, because it was originally uncovered in a setup where all the flux was coming from the horizon, so in fractionalized phase. Now, of course, there's some debate as to whether this is really a Fermi surface, because later some calculations were done that showed that basically there's no degrees of freedom in the spectral density at finite momentum, which is exactly what you would expect for a Fermi surface. So if they're not there, then you sort of have a problem. But irrespective of that whole issue, another thing that you find is that if you calculate the entanglement entropy in other sort of phases, like forget about fractionalized, like cohesive phases, you have a charged condensate sitting in the bulk, then you still find the same thing, and you still find that for theta equal d minus 1, this scales logarithmically, which means that the entanglement entropy is an observable which is completely blind to the details of the system in that respect. There was a proposal to try to remedy that state of affairs. Could you devise some sort of non-local quantity which would know about where the electric flux is coming from? And the proposal was simply to deform the usual entanglement entropy by the contribution from the electric flux through your subsystem in the boundary. So for fractionalized phases, this doesn't change anything, because this phi gamma here would just be a constant. So when you would minimize that, this would just drop out. But for fractionalized phases, cohesive phases, when the electric flux doesn't come from the horizon, then you might hope that, well, this would change, for instance, the minimal surface that you would get, or the scaling that you would get as well. So in this paper, Sean and Radicevic looked at phases where you had a constant charge density. They were already finding that there was some difference. But actually, if you carry out the calculation for generic phases, where you're not imposing any particular scaling on the charge density in the IR, then you find again that there's two very clear separations that involve this cohesion exponent, which tells you how the electric flux behaves. And basically, if it's low enough, then you will find that the usual scaling applies. You find the same minimal surface as in the Ryu-Takayama prescription, and you find that this term, even if this term is non-trivial, the Ryu term always dominates. That's why you get the minimal surface, the same as in Ryu-Takayama. But on the other hand, if the cohesion exponent is large enough, then you find that the scaling changes, and the minimal surface is no longer Ryu-Takayama. So those sort of observables are sensitive to those sort of behaviors, but then it would be good to give them a sharper field theory interpretations and maybe look at other non-local observables that have been suggested. Yes.
The second case, the scaling suggests longer range, goes faster than the area.
In the second case, yes, the contribution, the main contribution comes from that term. So it really dominates this observable. Okay.
So, yeah, just to get. I find a kind of deception, right? That theta is the minus one, it's just a Marshall point out there.
Yes.
A whole class of methods out there that go faster than sigma log sigma, right?
Mm-hmm.
They tend to follow.
Yeah.
And you find here the same thing. So
yeah, exactly. So, right, in summary, so I've told you how you could classify cohesive phases which are translationally invariant, and you can do that by introducing 4 exponents, which is not too bad, I guess. Those new exponents, conduction and cohesion, typically occur in the scaling dimensions of infrared operators. You see them also appearing in the optical conductivity. you can check on very general grounds that thermodynamic stability implies that you have a gapless spectrum, so that's pretty nice. And the remaining questions is, can you find traces of these exponents in other observables and generalize these sort of pictures to more complicated situations like what Elias was telling you about on Wednesday? Thank you.
One quick question. So maybe I know it's impossible to answer, but can you say something about if it's possible to find boundary field theories? Because you start with an effective gravity theory, right? Whether it's possible to embed that in some string theory or something.
Well, right, so I've not really put the accent on that, but yeah. The sort of theory that I'm looking at, there are points in the phase space for specific, so I'm letting these scalar couplings be completely arbitrary functions. The only thing I'm assuming is that if there is an asymptotic branch, I want to be able to describe that with an exponential. So there's a whole host of top-down models where you can just pick you will get this sort of potentials with exponentials. And like Chen-Simons coupling, I mean, Jerome and Aristos have a large number of models which will reduce to these sort of actions, even the massive vector models. So yeah, I mean.
Okay. Then if not, let's say this game.